Okay. So before starting, a couple of announcements. So we have already set this on Teams, and possibly all of you have seen it still. So since many of you requested, we have extended the deadline of lab assignment 4 to Sunday, right? And you need to fix a time with the TAs between March 4 and 7 in order to get your assignments evaluated. Also, the next assignment has been given on Moodle, right? So this is going to be a 2-week assignment, and this is a simpler assignment, as in it does not involve PintOS and all. So it involves things which we are discussing now, as in uh, now and the last week, as in how different processes or threads can access the same shared memories, how to deal with synchronization issues, and so on. Right. So, but again, this is an assignment where you will be basically using the OS as an API. So you will be using some system calls for creating semaphores or uh, mutex calls between threads and so on. So some of the function calls which we have discussed or we are going to discuss in the theory class will be useful there, right? So, but this is likely to be a simpler assignment. So make sure you do, I mean, you check assignment 5 and do that also. Okay, and since we have declared the assignment already, so there won't be a live lab session today. Of course, if you have any queries about the assignments, feel free to use Teams, the lab discussion channel, and ask. Okay, so let's continue from what we were discussing. So we were discussing semaphores, right? And just a 2-minute recap. We have understood that semaphore is an integer intuitively. Semaphore is an integer which has basically 3 operations on it. Okay, okay, 4. I mean, you can initialize it and delete it, fine. Apart from that, the main 2 options are wait and signal, sometimes called P and V. So basically, wait is you try to reduce the value of the semaphore by 1, which essentially indicates that you are as if grabbing a resource or grabbing a lock. And signal is you try to increase the value of the semaphore by 1, which essentially means you are trying to release a resource or release a lock. However, this is the very intuitive definition of semaphore. A more actual definition is what we discussed towards the end of yesterday's class. It's actually a value and a process list, a list of processes which are waiting on this semaphore, right? And this is what we discussed. These are the pseudocodes for wait and signal. So for wait, you will try to reduce the value by 1. I mean, you will reduce the process we're calling wait will reduce the value of semaphore by 1. And if the semaphore is not available, that means if the value of s is less than 0, then this process will be added to the list of processes waiting for that semaphore. And then this process will block. This is important because this prevents busy waiting. Okay. Similarly, for signal, the process calling signal will increase the semaphore value by 1. And if it is less than 0, if the value is less than equal to 0, then one process from the list of waiting processes will be woken up. That means, let's say, will be placed in the ready queue, because this process which we decide to wake up, this was waiting for the semaphore. Now the semaphore value has increased by 1. So at least one process should be given the lock. So this is a special kind of lock where actually you can think that there are many instances of the lock, and as long as one process gets one instance of the lock, it is sufficient. Of course, whether you are using it as multiple instances of a lock or as a single binary semaphore, that's up to you, the programmer. But semaphores can be used in different ways. We discussed some of the ways in which semaphores can be used. Okay, let's proceed. Any question till here? So this is where we had ended yesterday. Any questions? Okay, if not, let's proceed. So while dealing with semaphores, a particular situation can come up which you should avoid. Right? Let's see what the situation is. It's called deadlock. Okay. Actually, the next chapter will be on deadlock. We will do a much deeper study of deadlocks, but just this one slide to initiate the idea. So a deadlock happens when two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. Right? So processes often wait for events. Nothing like wrong in that. We have been discussing that throughout the semester. But here a process is waiting. So multiple processes are waiting for different events. However, those events are possible only by one of those waiting processes. So basically, since that process, which is so the say process P1 and P2 or P0 and P1, P0 is waiting for an event which can only happen by P1, and P1 is waiting for an event which can only happen by P0. Right? This is a deadlock. So basically, it's a kind of a stuck situation. Both processes are stuck. There cannot be any progress. Let's see this example here. Let's say we have two semaphores S and Q. Both are binary semaphores. Let's say initialize to 1. Now see these two code segments, P0 and P1. Assume that P0 called wait on S. Okay. So P0 is waiting on S. Then P0 was swapped out of the CPU. P1 came in. P1 was allocated the CPU. P1 called wait Q. It got the lock to Q. Now think about it. P1 to proceed, P1 now is requesting a wait on S, which cannot happen because P0 has already locked S. So P1 cannot proceed unless and until PO signals S. Okay. On the other hand, P0 now, when it next gets the CPU, calls wait Q. It gets blocked because P1 has already locked Q. And P0 cannot proceed unless P1 signals Q. So now basically P0 is waiting for an event which can only be caused by P1, and P1 is waiting for an event which can only be caused by P0. Basically both are stuck. They can be allocated CPUs many times, etc., etc., but then no one will be able to proceed. So basically deadlock leads to indefinite blocking. So in this particular case, a process will never be removed from the semaphore queue for which it is waiting, because the only process which can signal that semaphore is also waiting for this process itself. So if you are not careful about how you use semaphores or how you sequence the calls to wait signal, you can end up in such situations. This situation is called a deadlock. We will study much more on deadlocks in the next chapter, which will probably begin tomorrow. Okay, any questions? Okay, if not, let's proceed. Now that we have fairly understood what semaphores are, how like we have got some idea about how they are implemented and what can be some dangers, etc. Let us actually study some classical problems of synchronization. Right, so these are some kind of benchmark problems. So let's say someone comes up with a new mechanism of handling synchronization. Then the first thing that they should do is to prove that their solution works correctly for these classical problems. This happens so I think the word benchmark is kind of familiar. So like in many problems, there are these benchmarks kind of thing where if you come with a new solution, you have to first show that your solution works correctly on that benchmark. This can even happen to hardware. Like maybe you know that nowadays new processors come up, new GPUs come up. So there are these benchmark tasks where every GPU has to prove its performance. Right. So here these are some classical problems of synchronization where any new mechanism for synchronization or okay, I'm hearing Okay, hello. I think I got disconnected due to some network issues. Can you all hear me again? Okay. So, Ayush, can you unmute yourself? I want to know till when I was audible.
Sir, you started discussing the classical problems.
Okay, fine. So till deadlocks, you all are able to hear. Okay, fine, thanks. Okay. So yeah, so there are these classical problems of synchronization. If someone comes up with a new proposed solution for the critical section problem, they are supposed to demonstrate that their new solution works on these problems. These are kind of benchmarks. Okay. Specifically, let us study how semaphores can be used to solve these classical problems. Of course, we'll understand the classical problems and then see how semaphores are used. Okay, first thing is the bounded buffer problem, which we have actually discussed. Let me just quickly do a recap. So there is this producer and a consumer process. Actually, there can be several producers and several consumers also. So producers will produce some items in a shared buffer and consumers will read those items from the shared buffer. And the idea is to synchronize between these producers and consumers because there are these practical limitations that unless the producer has produced items, there is no point for the consumer to try to read them. Right? Also, maybe for some reason the consumer is slow. Right? So the producer is producing items very fast, but the consumer is slow. So somehow the producer should understand that the buffer is getting full, and so it should wait. Since you are also doing a networks course, you will come across very similar concepts in networks course also. Have you already come across such concepts in network course where maybe a sender and a receiver needs to synchronize their speeds? So it should not be that the sender is going on sending data too fast and the receiver is not even able to get theirs. Yeah, so it seems that you have come across these concepts in networks also. Yeah, exactly. The sliding window mechanisms and those kind of things. Yes. So yeah, so here we are not talking about remote processes, but we are talking about the same process, multiple processes in the same computer. Okay. So the network problem is a larger version of this problem where um, the producer and the consumer are in two different systems. So the only way they can communicate is via the network. But here it's not so. Here we are, yeah, congestion control, exactly. So here we are dealing with a slightly simpler situation where all processes are part of the same computer. Therefore, they can use IPC, like inter-process communication or synchronization to synchronize. So what in this case, what is a possible solution? Let's say we have n buffers, right? So we have already discussed this problem. So there are n buffers. We want to utilize all of them. So let's say we use three semaphores, mutex, full, and empty. So clearly, mutex would be used for for ensuring mutual exclusion to the buffer. See, the issue is that multiple readers can access the buffer at the same time, but then multiple producers should not be allowed to write to the buffer at the same time because that might create some race condition. Right? So I hope you understand this. So mutex is for ensuring mutual exclusion, and empty and full are for counting the number of empty and full buffers. So let us see how the process will move using these semaphores. So this is the basic structure for the producer process. Okay. So it will produce an item and then it will wait for empty. So what does this basically mean? Waiting for empty, intuitively, what does it mean? Wait empty, what does it mean? Remember in the previous slide we said empty will be initialized to the value n, which is the number of buffers. So intuitively, what does wait empty, what is the producer trying to do here? Exactly what Sriharsh said. Basically, we are, I mean, the producer is trying to ensure that at least there is one buffer slot empty. Right? Yeah, Pankaj also said the same thing. So yeah, Soumitra also. Yeah, it's trying to ensure that at least one buffer slot is empty, because we will see the corresponding consumer process in the next slide. But intuitively you understand that every time the consumer consumes an item, it will signal empty. Right? So it will indicate that yes, one buffer slot is now empty. I have already read the data. The consumer will indicate. That is what the producer is waiting for. Once it gets the empty lock, empty semaphore, that means at least one buffer is empty, one buffer slot is empty, then it will wait for mutex. Because again, we want mutual exclusion while accessing the uh, shared buffer. As I said, if you have multiple readers, it is conceivable that multiple readers do not need mutual exclusion while accessing the buffer. But then the moment you have a producer, then mutual exclusion should be ensured, because when the producer is in the middle of updating the buffer, then the reader, any consumer should not try to read it. Okay. So it is waiting for both these semaphores, first empty and then mutex. When it has got both, then it adds the next produce to the buffer, and then it signals mutex and full. Okay, so this goes on in a loop. Let's go to the consumer process, then I can ask for questions. Now this is the corresponding consumer process, which is kind of a mirror image if you think. So this first waits on full. Again, so here the consumer is trying to ensure that at least one item is there in the buffer, because see in the previous slide producer process, after filling in one item in the buffer, the producer signaled full. So that is what the consumer is waiting for. Once it gets that, that means at least one item is there in the buffer, then it waits for mutex, then it removes the item, then it signals mutex and then signals empty. So this is the structure of the producer and consumer. Any questions? Okay, good. So I mean, if no questions, we will proceed to the next problem. Okay. So the next problem is kind of similar, but slightly more complicated. It's called a readers writers problem. So actually, if you think about it, in the classical definition of producer consumer problem, there is one producer and one consumer. But the readers writers problem is a more complicated version, where there are multiple readers and writers. So a dataset is shared among a number of concurrent processes. The readers only read the data. They do not change anything in the data. Writers can both read and write. And the problem definition says that multiple readers can be allowed to read at the same time because they are not updating anything. So there is no danger of the process, I mean the shared memory getting corrupted or a rest condition happening. But a writer must have exclusive access to the shared data while writing. So when a writer is writing, no reader should read the data. Also, remember there are multiple writers. So when one writer is writing, other writers also should not be allowed to write anything. Okay. So if you think conceptually, this is a more complicated version of the producer consumer problem. Now, also, this is a very well-known problem and there are several variants. The variations are based on how readers and writers are prioritized. So let's understand. So let's just briefly discuss two variations. In the first variation, this is the definition. No reader should be kept waiting unless the writer has already obtained permission to use shared dataset. So no reader should be kept waiting unless a writer has already obtained permission to use the shared dataset. Means that one reader should not have to wait for another reader, simply because a writer is waiting, right? So basically what does this mean? In this very first variation, readers are given priority, whereas writers can starve a bit. Okay. So yeah, no reader is kept waiting for another reader just because a writer has already, sorry, no reader is kept waiting unless the writer is already writing into the shared dataset, or the writer has already obtained permission to use the shared dataset. Right. So basically, let's say in a certain condition, 5 readers are waiting and also 1 writer is waiting. So the readers should be given priority. Right. That's the first variation. Second variation is this. Once writer is ready, it should be allowed to perform the write as soon as possible. So here you understand writer has priority. It's okay for the readers to wait a bit. So there is no correct wrong here. It's just based on your application, you will choose one of the variations. And both can have starvation problem, as in the first variation, writer can starve. In the second variation, readers can starve. But again, it's up to you which variation you choose. We will specifically discuss the first variation here. Okay. So is the setup clear? Great. Okay. So now these are the semaphores that we will go with. Okay. So semaphore RW mutex, which is initialized to 1. Semaphore mutex initialized to 1 and integer read count initialized to 0. Specifically, RW mutex will be used for the writers. So mutual exclusion semaphore for writers. And mutex will be used to ensure mutual exclusion when read count is updated. Understand clearly what is happening? This is a complicated scenario, so think about it. So we have already a shared dataset. Okay, we have already a shared dataset. RW mutex is used to ensure mutual exclusion when accessing that shared dataset, specifically for writers. See, that way, think about it intuitively. Suppose only 5 readers want to read the dataset. There is no need for mutual exclusion. They can read concurrently even, because writers are not changing anything. The problem happens when writers are writing. Okay, I may have told something wrongly. Let me correct. I forgot what I told. When 5 readers are trying to read the shared dataset, there is no need for mutual exclusion. They can be allowed to read concurrently. But the problem occurs when a writer is trying to change it. Then there should be mutual exclusion. So this RW mutex is basically used for mutual exclusion among the writers. Also, there is this integer read count. We will see what it does, but according to this solution, this semaphore mutex is used to ensure mutual exclusion when read count is updated. Okay, we will see. Again, I'm not claiming that this is the only solution to the readers writers problem. You can come up with new solutions. This is the solution which the textbook gives. That's why we are discussing it. But if you look up the literature, maybe other solutions also exist for the readers writers problem. Okay, so let's see. This is the structure of a writer process. Very simple. It simply waits for the RW mutex. Once it gets the semaphore, it writes and then signals. Okay, very simple. Now the consumer process, the reader process is more complicated, which I'll show in the next slide. I want you to understand that, and also the next slide has a question. So I want you to understand the reader process and then answer that question. So this is the structure of a reader process. It seems a bit complicated, but try to understand. And if you have understood, then answer this question at the site. Take 5 minutes. It's okay. Okay, even before you think of that question, maybe another question from my side. What is the role of read count? What is the role of this variable here, read count? By the way, this should also be read count. The underscore got missing, sorry. So yeah, basically read count. So what is the role of read count? So we do read count plus plus here and read count minus minus here. What is going on? Yes, Pankaj has the answer. It's basically, think about it, but possibly it is keeping a note of how many readers are actually want to reading. I mean, how many readers want to read the shared data. Okay, so I hope that part is clear. What is the role of read count? Okay, now I see some of you already trying to answer the question which is written on the slide. So yeah, maybe. So Shomitra says that, okay, the question is that if a writer says already in the critical section, so then all readers must should wait, right? So let's say n readers are waiting. So which readers are waiting on which semaphore, or which readers are queued up on which semaphore? So Shomitra is saying the first reader is waiting on RW mutex and the rest are all waiting on mutex. Which is saying, okay, okay, okay. Maybe Vij has, I think Vij tried to answer both the questions together. So yeah, I mean, but basically Shomitra and Vij both are telling the same thing. So let's see the answer. Yeah. So what Shomitra said and maybe Vij also wanted to point out. Yeah, that's the thing. Yeah, Pankaj also. So it's good that you are understanding, some of you, and answering, but I mean others see that if it is clear or if you have any questions, ask. So basically the read count variable is meant for keeping a note of How many readers at this point want to read the buffer? Right, and if a writer is already in the critical section, then this is the situation, what is written here now. So if any one of you have any question, then write here, please. Okay, looks good. Fine. Now let's proceed. So this is the readers writers problem. This is one variation of it. Feel free to look up the literature on other variations, and as I said, also possibly other solutions might also be proposed. I'm not sure. Okay, and if you still need some further explanation, do look up the book. The book kind of explains things. Okay, we have a question. Shomnath is asking, does it mean that if the first reader sees that RW mutex is free, okay, then now all readers can read as it signals mutex? Okay, others, what do you think is the answer? What was mutex initialized with? Let's go back. Mutex was initialized to 1. Okay, mutex initialized to 1. So first thing to note is that this signal mutex step is not under this if. Okay, so think about it. This signal mutex is not under this if, right? So if read count equal to 1, it's wait for RW mutex. But this signal, but irrespective of whether this happens or not, this process will signal mutex. So what is mutex actually used for? This was written in the 2 slides back. Mutex is used to ensure mutual exclusion when read count is updated. Yeah, what Shubham and Pankaj are saying. So mutex is used to ensure mutual exclusion when read count is updated. Okay. So then, what is the answer to the question by Shomnath? Maybe let's hear someone say, Pankaj, what do you think? Like unmute yourself and say.
Hello. Sir, I'm audible.
Yeah.
Yeah, I think because the readers have priorities. So if the first reader is not waiting on the writer mutex, like RW mutex, not waiting for writer, so even others need not wait. because they can also basically at this point the writers and few other readers are trying to access the same shared data, and the first reader didn't need to wait for the writer, so others also need not wait. But that will only happen after it signals the mutex.
Just a minute. Why do you say that the first reader did not have to wait for the writer? It is waiting for the writer, right? If read count equal to 1, wait for RW mutex. And the writer can, the writer can lock RW mutex.
But that is given in his condition. Like Somnath mentioned that RW mutex is free.
Ah, okay. Yeah. Okay, that makes sense. Yes. Okay.
Yeah, that's it.
Hello.
Hello. Yeah. So that's it. Yes.
Okay. Yeah. So basically, like it's important to distinguish between the role of RW mutex and mutex. Mutex actually is not controlling access to the shared data. Mutex is controlling access to this read count variable, right? Whereas RW mutex is the one which is controlling access to the shared data, right? So think about it. Maybe if this discussion that did not make sense, then think about it. Maybe read the book a bit more. It contains a better description of the reader-writer problem. But yeah, the mutex semaphore here, this is meant to ensure that the readers, when they are updating read count, they do not create any read condition. So basically readers are not creating any, readers, there is no scope for readers to create a read race condition on the shared buffer because they are not even trying to modify that buffer. But for a particular reason, it needs to be known how many readers are waiting to read from the buffer. And that is why this read count variable is necessary. Right? And why do you think this is necessary? That why do you actually need to know that how many readers are waiting for reading for the buffer? Exactly what Shubham Somnath is pointing. That complicacy is because what we have decided, this thing, that readers should have priority, right? So we can only allow to write only, we can allow to write only if there are no readers reading. So if this was not the case, then maybe this solution would have been simpler. But because we have taken this like assumption, or I might say a constraint, or that is the condition that we have decided to go by in this first variation of the readers writers problem. Because of this, we need this variable read count to understand how many readers are wanting to read from the data. Because a writer should not be allowed to write in the data in the shared data if some readers are waiting already. Okay. So think about it. Maybe spend some more time, go through the book, then I think it will make sense. Okay. I hope so. Possibly some of you have already understood. For the others, go through the book and see, it will make sense. Okay. In the interest of time, let me just go ahead to the next problem, which is kind of simpler. So it's called a dining philosopher's problem. Okay. So here the book says that, let me repeat that this is not to make fun of philosophers, etc. Computer scientists don't have any enmity or animosity with philosophers. But yeah, that is how, for some reason, the problem became famous, dining philosopher's problem. So philosophers spend their lives alternating between thinking and eating. So there are 5, let's say in this case 5, but some number n philosophers sitting in a round table. Before each of them, there is a rice bowl. Okay. They spend their lives alternating between thinking and eating. So they do not interact with their neighbors. They're just thinking, and sometimes they feel hungry, they eat. So when hungry, okay, so in front of them, they have these 5 rice bowls. But the issue is they have these 5 chopsticks. Now, chopsticks, I guess you know, like in Japanese or even Chinese culture, it's used. So when hungry, they try to pick up the 2 chopsticks one at a time to eat from the bowl. Now they need both chopsticks to eat. You cannot eat with one chopstick. It's not like a spoon. So they need both chopsticks to eat, and then they release both when done. So understand this, that there is no, there is no competition with the rice, because every philosopher has his or her own rice bowl. The competition, if you may say so, is for these chopsticks. There are 5 people and 5 chopsticks. And everyone, when they want to eat, need 2 chopsticks. So if this person, this lower person wants to eat, they would try to grab, or he or she would try to grab these 2 chopsticks. But that is the kind of the competition, 5 people and 5 chopsticks. Ideally it would have been 5 people and 10 chopsticks, but no, there are only 5 chopsticks. So now the chopstick is what has to be synchronized, access to the chopsticks, right? And also these philosophers don't interact with their neighbors. So it's not that they decide that, oh, first you eat, then I'll eat, nothing like that, right? So basically you can assume that there is one type of resource, which is chopstick, and you have 5 instances of that. So let's say we define a semaphore, a counting semaphore, or okay, sorry, here they are initializing 5 binary semaphores. So since there are 5 chopsticks, 5 binary semaphores are initialized to 1. By the way, we are going ahead with 5. It can be more actually, right? So basically, as many philosophers are there, there will be that many rice bowls. So no competition there, but there are the same number of chopsticks, and therefore the competition. So this is what philosopher I does. Okay, and again I have a question for you, if you understand. Philosopher I waits for chopstick I, and then waits for chopstick I plus 1 modulo 5. Right, so basically, so this I guess you understand that the philosopher 0 is waiting for chopstick 0 and 1. Philosopher 1 is waiting for chopstick 1 and 2, and so on. But philosopher 5 is waiting for chopstick 5 and okay, 0, 1, 2, 3, 4, sorry. So philosopher 4 is waiting for chopstick 4 and 0. Right, that's I plus 1 modulo 5. So they wait for these 2 chopsticks, and then they eat for a while. Then they signal the 2 chopsticks. Then they again think for a while. So this is the remainder section if you think. So they are not trying to access the shared resources here. This is what they do. Simple. But then there is a problem with this algorithm. What is that? If you have any question, ask. Otherwise, my question is that what is the problem with this algorithm? Okay, so okay, one thing. Ayud is saying the philosopher might wait even when there are 2 free chopsticks. Okay, see one thing. So Ayud, that's not a problem. That is how we have defined the problem. I mean, that's not a problem with this algorithm. That is how we have defined this dining philosopher's problem. We could have said that there are 5 chopsticks. Any philosopher can simply grab any chopstick. But we are not telling that. We are telling that, say, this philosopher who is at the lowest end of the table. I mean, looking at the slide, of course, a round table does not have any lowest end. But looking at the slide, this philosopher will only try to access these 2 chopsticks. Even if these 2 are free, even if the upper 2 chopsticks are free, this philosopher won't try to jump and grab those 2 chopsticks. Right, so that is not the problem with the algorithm. That is how we are defining the situation. Okay. that you are right. A philosopher might wait even when there are two free chopsticks. But then that is how we have defined it. A philosopher will only try to access the two chopsticks closest to him or her. Okay, so now I see that Shomnath's answer, Pankaj's answer. What did Srihash said? Okay, so okay, yeah. So basically, okay, maybe Srihash also tried to say the same thing, but then yeah, I mean I clearly understand that Pankaj's answer same what Soumitra also said. Suppose that suppose let's say every philosopher executed this instruction, and then the processor was allocated to another philosopher. So philosopher I came, executed this instruction. Processor was allocated to philosopher 0. Philosopher 0 came, got hold of chopstick 0. CPU got allocated to processor 1. Processor 1 came, grabbed chopstick 1. Processor is allocated to philosopher 2, and so on. So it can happen that every philosopher grabs one chopstick. Right? Going back to the picture, so every philosopher grabs his or her left chopstick. So now there is a deadlock, because every philosopher is waiting for another chopstick, but that chopstick can only be released by another philosopher who is also waiting. Okay, that is the problem. So basically all philosophers can starve to that. Right? Now what can be solutions? There are many possible solutions, some of which are written in this slide. So you might say allow at most 4 philosophers to be sitting. So basically have one extra chopstick, so that at least one person will have 2 by pigeonhole principle. Or you might say that you might have some other constraints, like a philosopher should pick up the chopsticks only if both are available. There is no point in grabbing one, because you won't be able to do anything with one. Or we can even think of an asymmetric algorithm, like an odd numbered philosopher first picks up the left chopstick and then the right chopstick. Even numbered philosopher picks up first the right chopstick and left chopstick, and so on. Right. But it's good that some of you understood the problem, that yes, this can lead to a deadlock. Okay, so yeah, there are many different solutions possible. Right. So basically you understand that there can be some problems with semaphores if you are not careful in using them. So okay, first of all, okay, something is okay. Okay, this slide. Okay, fine. So one thing is that, yeah, like calling signal before wait is a mistake. Okay, it might not be a mistake. It might actually be what you want. Actually, we discussed something like this. Do you remember? Something we discussed yesterday. At some point, signal actually might happen before wait. Anyone remembers? Okay, there was this thing where we were telling that there are two processes, P1 and P2, and P1 contains a statement S1, P2 contains a statement S2. We want to ensure that S1 executes before S2. Right, so the solution we discussed is after S1 is executed, P1 will signal mutex or some lock. P2 will wait for that and then execute S2. So yeah, I mean, of course, depending on the application, signal can happen before mutex. Sorry, signal can happen before wait. But yeah, I mean, that you have to be careful. Yeah, and also the main problem is this, that if you are, I mean, you might not be aware that your solution has a possibility of deadlock. Like in general, when we saw the solution for the guiding philosopher's problem, it seemed okay. But then if you think carefully, it can happen that only this got executed, and then a deadlock can arise. So you'll have to be careful about how semaphores are used. Okay. Okay. Fine. Okay. Let me just take 2 or 3 minutes because I mean this topic is about to end. Yeah. So a very brief discussion on what. So till now we were discussing semaphores intuitively or the concepts behind them. A very brief discussion on what Linux offers. As usual, I'll just tell you some names of some system calls or names of some functions. We expect you to figure out the details. So actually Linux provides semaphores, spin locks, etc. Let's focus on semaphores. Again, if you remember that POSIX library we discussed when discussing threads. So POSIX also, gives semaphores. As in POSIX, the POSIX standard defines how semaphores should work. Now it's up to the operating systems to implement them. So Linux implements semaphores. You have to hash include semaphore.h, and you have to compile the thread. Okay, this is slightly mistaken. Sorry. If you have threads, then you have to compile using -l pre-thread. Otherwise, it's not necessary. Okay. But okay, how do you work with a semaphore? Basically, this is the data type sem_t. This is the data type for a semaphore. So this is how you declare a semaphore, and then you can initialize it using the sem_init function. So this is the semaphore to be initialized. You send a pointer to it. Then there are kind of these two arguments. This is the simple value. So the initial value of the semaphore. We discussed that in certain situations you can go for a binary semaphore. So maybe you will initialize with 0 or 1, or you may even go for a counting semaphore where you can even initialize with 5. That's up to you. Also, there is this thing p shared. This I leave it to you to figure out the details, but just see what is written here. So actually semaphores can be used both among processes or among threads of a particular process. Right? So this argument here will tell what you want. You want the semaphore to be accessible across processes, or you want the semaphore to be shared only by threads belonging to this process. Actually, if you see the new lab assignment that has been declared, assignment 5, you will see that we have asked you to do the same problem using processes and threads. So it's up to you how you decide to do. We have given you that flexibility, but then you should design how you want to do. So these are tools which Linux gives you. Okay. Okay, and then you have these operations. You wait on a semaphore using semWait. You signal a semaphore using semPost. And then you can destroy a semaphore using semDestroy. Okay. So these are pretty simple functions to use. So how you use the semaphore, that is the challenge. So that's up to you, as in depending on the application you are doing. Okay, so that ends this chapter on process synchronization, just with a summary. So we understood the problem, what we are trying to solve here, which is called race condition. Right, and also like it's kind of, okay, race condition and critical section problem are not the same, but yeah, I guess you understand the relationship between the two. So every process has a critical section where it will update shared variables or shared data structures, and protecting that critical section problem is what we discussed. Mutual exclusion, remember, mutual exclusion is not the only requirement. There are other requirements like bounded waiting, progress, and so on. And then we discussed various solutions to the critical section problem. We started with a completely algorithmic or software solution called Peterson's algorithm. But then we discussed a problem that just software solutions are not enough. In modern architectures, there is often out of order execution of instructions and so on. And due to these, only a software solution is not enough. So in some way, you need hardware support. That means you need special atomic instructions, which is guaranteed that there won't be any preemption while that instruction is being executed. As a precursor to this, we understood that things that we write in a high-level language, say X++, that is actually not one instruction. If you think of assembly language or machine language. So X++ can be broken down into 3 instructions, and there can be a preemption in between these 3. However, there are these special atomic instructions which guarantee that there will be no preemption within that instruction. And then we discuss mutex locks and semaphores, which are closer to the programming. Like the special atomic instructions are usually actually hardware instructions. Like the MIPS architecture can give several atomic instructions, or any architecture gives atomic instructions. But while writing a program, we would not possibly like to use that kind of a hardware instruction. So therefore, we use mutex locks or semaphores and so on. Okay. Fine. So that's all in this chapter. I have nothing more here. If you have any questions, you can ask, or if not, you can leave. Okay, you have Sriharsh says, I have a question regarding in the implementation of wait. Let's go back to that slide. Yeah. So your question is, wouldn't these cause an issue? The sequence occurs. Okay, let's understand. Give me some time. Okay, Sriharsh, please unmute yourself. At the 4th step, why do you think P1 will be allowed to enter the critical section? Because P3 has already called wait.
Yes, sir. So P3 has called wait and it has entered its critical section. But when it gets preempted, for example, and P1 gets the CPU, it continues after the block statement, right? It's not checking for the value of the semaphore. It assumes that the semaphore has been released since it has been woken up directly. So it returns from the wait call and continues into the critical section, right? I think there should be a while loop where we're checking for the S value, negative.
Okay, let me understand. You are saying, so suppose P1 had, P1 had once called wait. And then, so it was like added to the ready queue. I'm sorry, added to the queue of the semaphore. Then, okay, some other process signaled this semaphore. So P1 was returned to the ready queue. But before it could get the semaphore, another person called wait, or another process called wait. Yeah. Then you are saying when P1 will be allocated the CPU, it will so okay, basically you are kind of assuming that okay, I would think that your question has more to do with how block and wake up are implemented. So you are assuming that when P1, so P1 got blocked at some point, then this way, I mean, say wake up wake up P1 happened, right? So then you are assuming that when P1 has been returned to the ready queue, it will not check for the semaphore again, right?
Basically, when P1 gets the CPU again, it's not checking, right? So because after the if there's no statement that checks the S value again, it just returns from the wait call.
Yeah, but so correct me if I'm wrong, but it seems that you are assuming that, so since you said P2 had signaled, so P2 has signaled, wait, what happened? Power went off. Okay. Okay, there might have been a power cut. Okay, so, okay, I need to pack up in 5 minutes, but let's see. Yeah, so see again, okay, I'm hurrying because some power cut has happened. My computer is running on UPS, but the network will soon go. So I think I'm trying to say something similar to what Somnath is trying to say also. So Srihash, you are assuming that when P1 has woken up, it will not check the semaphore again. I'm not sure if this is correct. I don't think this is correct. So that's why I'm saying possibly your question. Hello, can you hear me?
Yes, sir, I can hear you.
Okay, so okay, I'll think more about it and come back. But I believe that just because this wake up is here does not mean that sure P will be returned to the ready state, but that does not mean that next P1 will be returned to the ready state, ready queue. But it does not mean that next time when P1 tries to enter the critical section, it will not wait for the semaphore again. Okay, so I think every time P1 tries to enter the critical section, it will check the value of S and call wait and so on.
Okay, so inside the P1 process, we're running wait in a loop. Is that the expectation?
That's up to you. Like, I mean, the semaphore cannot define that how the process will use wait in a while loop or not. So I think that your question has more to do with how block and wake up are implemented. Okay, Pankaj is saying if that is the case, then it might starve forever. So, okay, this is not called starvation. So, okay, fine. It might be, yes. So suppose there are hello, can you guys hear me still? I'm not sure when the network will go anyway.
Yes, sir.
Okay, so see, suppose there is one semaphore for which 100 processes are waiting. Then it can happen that every time, like before, say, even the processes can have priorities, I don't know. So it can happen that every time a process wants to acquire the semaphore, it finds it locked. So that way starvation can happen. But see, starvation and deadlock is not the same thing. Starvation is also an undesirable situation, but then the programmers or people who have designed the programs should take care of the fact that starvation does not happen. But deadlock is a problem without any solution, as in the more time even if you give more time, deadlock will never correct itself. Starvation can happen, but then people usually assume a few things, that maybe some higher priority processes are getting their job done. So at some point they will stop or they will terminate, and then the lower priority processes will get the resource. Sure, as long as there is a higher priority process in the system, the lower priority processes can starve. So remember, we discussed these things when we are discussing CPU scheduling, that often we have multiple queue scheduling where different processes with different priorities are arranged in different queues. Then we talked about processes being moved from one queue to another, because as we said that there is a like time factor also. So if a process has been executing since a long time, you might actually want to increase its priority so that it gets the resource. So these things can be done. So starvation can happen, but then it's up to the designer to deal with it, like to include something in the solution which prevents starvation. However, don't confuse deadlock with starvation. Deadlock is a situation which, if it comes, nothing can be done with it. Something can be done that we will study in the next chapter, but yeah, there is this difference between, so deadlock is a kind of a stuck situation. All processes are stuck. Starvation does not mean any process is stuck. Starvation means some other processes are getting the resource continually, so their work is being done, but maybe this one process is starving. Okay, so let's make the two situations different. But yes, again, coming back to Sriyash's question, let me think for a minute. Let me think for this day. I'll get back about this tomorrow. Okay.
Sir, I think Shubham and Somnath clarified it. Like my third point is not possible. Basically, I assume that after calling wait, if the value of the semaphore is 0 before calling wait, it can directly enter the critical section. But the check is happening after the decrement. So
sorry.
It's not possible for
wait. Just could you repeat once? Sorry.
Yes. So basically, when P3 calls wait, at that stage the semaphore value is initially 0 because P2 has signaled the semaphore, making it from -1 to 0. So P3 calls it with 0. First decrements the semaphore, and after decrementing checks for negative.
Yeah. So
P3
now since P3 has called wait and enters the critical section, so now the semaphore value is -1.
Yes, it's making the semaphore value -1 due to the decrement step, and then so P3 itself gets blocked. It shouldn't enter the critical section anyway. So that was the mistake that I made. I thought that P3 could enter the critical section, following which P4 would also enter. But then P3 itself will get blocked, and then P4 will get a chance to enter. P1 will get a chance to enter.
Okay, so since P1 had called wait, so it had already decremented it to -1.
Yes.
In the first step, then P2 signals it, so the value gets to 0.
Correct.
Then P3 calls wait.
Yeah.
So the value is -1 again. Therefore, P3 cannot enter the critical section.
Exactly. I made that mistake. I thought I didn't consider the in P3.
Okay. Yeah. Okay. Thanks, Shubham and Somnath, for clarifying. Yeah. Okay. Great. But yeah, but even then, okay. But yeah, I think Srihash raised one good point that about this block and wake up. Yeah, so once the process has been woken up, yeah, after that, it does. So once the process has been woken up, it goes to the ready queue. Fine. But does it mean that next time the CPU is allocated to this process, it will definitely be able to enter the critical section?
Sir, I believe that depends on the implementation. Like for this implementation, it seems like that's the case. But for the Pingthouse implementation, for example, they're running the check in a while loop. So even after waking up, it checks the semaphore. That's why I got confused actually.
Okay, I see. Okay, fine, good. That was a good discussion. Okay, thanks everyone. So let's end the class today. We will continue tomorrow.